For almost a century, the Big Bang has been our best explanation for how everything began. Space, time, matter, all expanding from a single point, about 13.8 billion years ago. But recently something unexpected happened. The James Webb Space Telescope, our most advanced window into the early universe, picked up light from objects so ancient, so massive, and so developed that some scientists began asking a wild question. Could these things be older than the Big Bang itself? That headline exploded online. But behind it is a real puzzle. Webb isn't breaking physics, but it is bending the limits of what our models can explain. These distant galaxies, seen as they were just a few 100 million years after the Big Bang, look far too mature for such a young universe. Either the universe built complex structures much faster than we thought, or we've missed something fundamental about how cosmic time unfolds. So what exactly did Webb see? Why did it spark talk of something older than the Big Bang? And what does this tell us about how the first light in the universe really formed? When the James Webb Space Telescope started sending back its first deep-field images, scientists expected to see faint smudges of infant galaxies, tiny, irregular collections of stars just beginning to form after the Big Bang. What they actually found looked completely different. Hidden in that red-shifted glow were galaxies that appeared far too bright, massive, and organised for their supposed age. Some of them seemed to have built up billions of stars in what, cosmologically speaking, was the blink of an eye. The light from these systems had travelled more than 13 billion years to reach us, meaning Webb was seeing them as they were less than a few 100 million years after the beginning of everything. That should have been the cosmic equivalent of a newborn. Instead, they looked like toddlers, already walking, already talking, and somehow much more developed than expected. The telescope's infrared eyes are designed for exactly this kind of discovery. Unlike visible light telescopes, Webb can pick up the stretched, reddened light from extremely distant objects. Because the universe has been expanding for billions of years, the light from its earliest moments has been pulled into longer wavelengths, invisible to human eyes but right in Webb's range. The result is like time travel. When we look at those tiny patches of sky, we're not seeing them as they are today, but as they were when the universe was only a few % of its current age. Every new deep exposure pushes that time boundary further back, peeling away layers of cosmic history that have never been visible before. The first time astronomers processed those deep fields, they noticed something odd. A few small red dots stood out, their brightness far exceeding expectations. At first, many assumed they were errors, maybe dust, image noise, or even foreground galaxies fooling the instruments. But follow-up data confirmed that these signals were real and extraordinarily distant. That was when the confusion began. According to current models, galaxies at such extreme distances shouldn't have had enough time to gather that much mass or form so many stars. The early universe should have been chaotic and sparse, filled mostly with hydrogen gas and a few scattered clumps of dark matter. And yet, Webb was showing galaxies that looked relatively mature, dense and even chemically evolved, containing elements like carbon and oxygen that require multiple generations of stars to create. This wasn't a single anomaly. It became a pattern. As more deep fields were analysed, the telescope kept uncovering galaxies with similar traits: bright, compact, and apparently old. If the measurements were accurate, it meant that some galaxies formed incredibly fast, within just a few dozen million years after the Big Bang. That's astonishingly early, given that the universe needed time for hydrogen to cool, condense, and ignite into stars. It would be like visiting a hospital nursery and finding a 10-year-old sitting among the newborns. The timelines didn't line up. Of course, in astronomy, brightness doesn't always equal size or age. A galaxy can look massive because of temporary bursts of star formation or even gravitational lensing, when light from a distant object is magnified by another galaxy in front of it. So scientists began double-checking every assumption. Was the brightness inflated by lensing? Were the redshifts accurate, or were they based on approximate colour data? Could dust or unusual star types be distorting the readings? In some cases, later analyses showed that initial distance estimates were slightly off, pulling the objects a bit closer in time. But even after corrections, a few galaxies still seemed uncomfortably old. This is where the older than the Big Bang phrase started creeping into social media. Some researchers noticed that when they modelled the light from these galaxies, the stars inside appeared to be hundreds of millions of years old, older than the age of the universe at the time their light was emitted. That's clearly impossible under standard cosmology, but it signaled a mismatch between observation and theory. Either the age estimates were flawed, or the early universe was forming stars much earlier than expected. News outlets and online commentators skipped over that nuance and went straight for the headline: James Webb finds galaxies older than the Big Bang. The actual science is more subtle. The telescope's instruments can measure how far away an object is based on how much its light has been stretched, but estimating the age of the stars inside requires modelling their brightness and colours. If the models assume the wrong mix of star types or dust levels, they can easily produce ages that don't make sense. Still, the data can't be dismissed entirely. Even if the galaxies aren't literally older than the Big Bang, they're undeniably more evolved than theory predicted for that epoch. Something, somewhere, is off, either in our assumptions about star formation, the physics of early matter, or the calibration of the models we use to interpret these ancient signals. That tension is exactly why Webb's findings are so fascinating. It's not that the telescope disproved the Big Bang, it's that it revealed a young universe far busier and more productive than we ever imagined. The earliest stars might have formed faster, burned hotter, and enriched their surroundings with heavy elements much sooner than the textbooks suggested. The telescope may also be catching glimpses of massive black holes that helped shape early galaxies, pulling gas together more efficiently and accelerating their growth. These discoveries don't undermine the idea of a cosmic beginning. They make that beginning even more dramatic. For scientists, this is the best kind of problem. It doesn't mean everything we know is wrong, it means there's more to learn. The challenge now is to explain how such massive, mature galaxies could have appeared so soon after the birth of the universe. Are we missing a key ingredient in how structure forms? Did the first stars behave differently than we thought? Or are we seeing new physics in action, something that changes how we understand time, matter, or even the expansion of space itself? Those are the questions driving the next wave of Webb observations. What's certain is that the telescope has already fulfilled its promise to push human understanding right to the edge of the observable universe, and maybe a little beyond our comfort zone. Its discoveries are forcing us to re-examine how everything began, not by tearing down the Big Bang, but by asking how, in such a short cosmic moment, the first sparks of complexity ignited. When people hear that the James Webb Space Telescope can look back in time, it can sound like a poetic exaggeration. But in astronomy, that phrase is literal. Every time you look at something far away, you're seeing it as it was in the past because light takes time to travel. The moon, for example, is about 1.25 light seconds away, so we see it as it was roughly a second ago. The sun is 8 light minutes away, so our view of it is already 8 minutes old. Now stretch that idea to billions of light years, and you're looking not just into the distant past of space, but into the earliest moments of the universe itself. That's what makes Webb different from any telescope before it. The light from the universe's first galaxies has been travelling toward us for over 13 billion years. During that journey, the universe itself has expanded. As it expanded, the light waves stretched out like elastic bands, shifting from the energetic blue and ultraviolet colours where they started into the faint red and infrared range that our eyes can't see. Astronomers call that stretching redshift. The higher the redshift, the further back in time you're looking. The most distant galaxies Webb observes have redshifts around 13 or 14, which corresponds to a time when the universe was less than 300 million years old. Understanding that redshift is crucial because it's what lets scientists build a timeline of cosmic history. If a galaxy's light is stretched by a certain amount, we can calculate how far away it is, and therefore how long that light has been travelling. This is what makes Webb a time machine. Each pixel in its deep field images represents an ancient echo of light that began its journey long before the Earth, the Sun, or even the Milky Way existed. When you look at one of Webb's photos, you're not seeing a snapshot of space as it is. You're seeing a layered record of cosmic evolution, with nearby galaxies appearing as they are now, and the faintest ones showing how everything began. But what makes this process so challenging is that those earliest galaxies are incredibly faint. Their light is stretched so much that it's almost invisible, buried in the infrared background. That's why Webb's design focused on collecting infrared light with unmatched sensitivity. Its gold-coated mirrors and precisely cooled detectors allow it to capture these faint glimmers without interference from its own heat. Even a tiny bit of warmth from the telescope would overwhelm the delicate signals it's trying to detect. That's why Webb orbits far from Earth, near a point called L2, where the Sun, Earth and Moon all stay on the same side of its shield. It's kept cold, stable and isolated, giving it the perfect conditions to stare into the deepest darkness. Every deep field image Webb produces is a time capsule. The longer it stares at one spot in the sky, the deeper it sees. Each faint dot could be a galaxy made of hundreds of billions of stars, all compressed into a patch of sky smaller than a grain of sand, held at arm's length. When astronomers analyse those dots, they don't just measure distance, they extract the chemical fingerprints hidden in the light. These fingerprints tell them what elements exist there. Hydrogen, helium, carbon, oxygen, maybe traces of heavier elements forged by early generations of stars. In that way, Webb isn't just looking back in time, it's reconstructing how matter evolved from simplicity to complexity, from a sea of hydrogen gas to the first building blocks of life. That's why the older than the Big Bang headlines are both fascinating and misleading. The telescope isn't finding things from before the universe began. It's revealing how quickly complexity appeared after it began. Every pixel of ancient light tells a story of transformation. Clouds of gas collapsing under gravity, igniting into the first stars. Those stars living, dying and seeding the next generation with heavier elements. Webb's images show us those early transformations in progress, almost as if we've opened a family photo album and discovered that the universe was more active, more creative, and more efficient in its youth than anyone expected. This look back in time concept also explains why it's so hard to define what now even means on a cosmic scale. The galaxy we're observing might no longer exist in the same form. It's billions of years older by the time its light reaches us. We're seeing a version of it that no longer exists. In a strange sense, astronomy is always archaeology. Every observation is a dig through time, uncovering fossils of light. Webb just happens to be digging deeper than any tool ever has. That depth is changing how cosmologists think about the universe's timeline. For decades, we assumed galaxies took hundreds of millions of years to form and grow large enough to shine brightly. Webb's findings suggest that process happened much faster. When we see those unexpectedly mature systems, we're not peering past the Big Bang. We're watching the universe speedrun its early chapters. In just a few 100 million years, it went from a uniform fog of gas to complex galaxies, stars, and possibly even black holes. That's like going from a single cell to a complex organism in record time. What's even more striking is that Webb's data are helping refine the Big Bang model itself. By measuring how light from these early galaxies is stretched, scientists can test the rate of cosmic expansion, compare it to the cosmic microwave background radiation background, and check whether the two stories align. So far, the results mostly agree, but the details are revealing small tensions, tiny mismatches that could lead to new insights about dark matter, dark energy, or the physics that govern the first fractions of a second after the Big Bang. In other words, Webb isn't showing us the end of a theory, it's showing us where that theory needs an update. The universe hasn't turned out to be smaller, younger, or broken, it's just more ambitious. The deeper we look, the more we realise that the Big Bang wasn't the end of a mystery, but the beginning of one. The light Webb captures doesn't challenge the idea that time and space began together. It challenges our assumptions about how quickly that new universe grew up. By the time those photons reach Webb's sensors, they've been travelling longer than Earth has existed. They carry information about events that shaped everything we see around us today. The elements in our bodies, the stars in our sky, the galaxies that stretch across the cosmos. That's what looking back in time really means. It's not just about distance or age. It's about seeing the story of creation unfold, one faint, ancient flicker of light at a time. Once scientists realised what the James Webb Space Telescope was actually showing them, the tone of excitement quickly shifted into disbelief. The galaxies Webb uncovered in the first few months after launch looked impossibly advanced for their age. According to every computer model built on decades of research, the early universe should have been dark, simple, and slow to form structure. Gravity had only just started pulling hydrogen and helium together. The first stars were supposed to ignite after a long, quiet period known as the cosmic dark ages. But Webb's images seem to skip that slow build-up entirely. The telescope was seeing fully formed galaxies shining brightly just a few 100 million years after the Big Bang. It was as if someone had pressed fast forward on the timeline of creation To understand why that's such a big deal, it helps to look at what theory predicted. In the standard picture, after the Big Bang, the universe expanded and cooled. Roughly 380,000 years later, atoms formed and light could finally travel freely, leaving behind the cosmic microwave background. Then came the Dark Ages, hundreds of millions of years, where the universe was filled with neutral hydrogen gas and no stars. Slowly, small fluctuations in density caused matter to clump under gravity. These clumps grew, merged, and eventually triggered the first star formation. The first galaxies were expected to be small and irregular, like cosmic prototypes. Over time, through mergers and accretion, they would grow into the large spiral and elliptical galaxies we see today. But Webb's early images showed something that didn't fit that evolutionary ladder. Instead of tiny, dim clumps, it revealed bright, compact galaxies that already contained heavy elements that require several generations of stars to create. Some even appeared to be forming stars at rates 100 times higher than what our models said was possible so soon after the Big Bang. The implication was startling. Either the universe had a mechanism for creating structure far more efficiently than anyone realized, or the data were being misread in some fundamental way. Scientists began checking everything. They looked at the calibration of the telescope's instruments, the models used to interpret the light, and even the cosmological constants that define the age and expansion rate of the universe. One possibility was that the galaxy's brightness made them appear more massive than they were. If they contained many young, hot stars, their light could mimic the glow of a larger, older system. Another explanation was that the dust content or the chemical composition of those galaxies affected the colour of their light, fooling the age estimates. There were even suggestions that gravitational lensing, when a closer object magnifies a more distant one, might be exaggerating their apparent size. Still, after months of reanalysis, some galaxies remained stubbornly impossible. They were too big, too heavy, and too chemically mature to have formed in the tiny window of time available. To put it in perspective, imagine trying to build a city the size of New York in a week, starting from scratch. The physics just don't add up, unless something about the rules is different from what we thought. And that possibility, however remote, was what made the discovery so captivating. This is where the headlines got carried away. When some researchers noted that their models gave these galaxies stellar populations older than the universe was at the time, that was a mathematical shorthand, not a literal claim. It meant the models couldn't fit the data without producing an impossible result. But to the public, it sounded like the telescope had glimpsed something that existed before time itself. That's how older than the Big Bang became a meme. In reality, no astronomer seriously thinks these galaxies predate the Big Bang. What they think is that the early universe was more productive than we realized, forming stars and heavy elements at lightning speed. So why might the universe have developed faster? One idea involves dark matter, the invisible material that makes up most of the universe's mass. Dark matter clumps under gravity, and those clumps act as scaffolding where gas can collect and form stars. If dark matter behaved differently in the early universe, or if it formed denser concentrations than our models assumed, it could have jump-started galaxy formation. Another idea is that the first stars, sometimes called population 3 stars, were extremely massive and short-lived, burning hot and dying quickly in powerful supernovae. Those explosions would have seeded their surroundings with heavier elements and triggered rapid star formation in nearby gas clouds. In that case, galaxies could appear chemically mature, even though they were very young. There's also the possibility that our understanding of how galaxies grow through mergers needs adjusting. The early universe was small and dense, meaning galaxies were much closer together. Collisions would have been common. A series of rapid mergers could build a large, bright galaxy surprisingly quickly. But even that scenario strains the timeline, because mergers take time and energy, and there's only so much of both available in the universe's first few 100 million years. Another question that Webb's data raises concerns black holes. Some of these early galaxies may host massive black holes at their centres, perhaps millions of times the mass of the Sun. Those black holes could have acted as gravitational anchors, pulling gas inward and fueling intense star formation. Yet that creates another puzzle. How could black holes that big form so early? According to standard models, black holes grow by feeding on gas and merging with others, a process that takes time. Seeing giant ones in the first few 100 million years suggests that either black holes can form directly from collapsing gas clouds, or that they started larger than we ever thought possible. All these possibilities show how one telescope can reopen fundamental questions about cosmic history. When Webb launched, scientists expected refinements, not revolutions. Instead, it handed them a set of results that made them reconsider the pace of cosmic evolution. None of this undermines the Big Bang itself. It just means that the timeline we've been using might need stretching or reshaping. The beginning still stands, but the story between the beginning and the present is turning out to be a lot more complicated. For the general public, this might sound like chaos, scientists changing their minds again. But that's how science works. When data don't fit theory, you don't ignore the data. You test, you recalculate, and you build better theories. Webb has forced cosmologists to confront an early universe that was not quiet and slow, but energetic and creative. Galaxies that should have taken 1 billion years to mature were already thriving when the universe was less than 3% of its current age. If anything, that makes the story of creation even more impressive. The Big Bang didn't just give rise to space and time, it set off a chain of events so efficient that within a few cosmic heartbeats, matter organised itself into glowing islands of light. These are the impossible galaxies Webb has shown us. Not relics of a universe before time, but proof that the early cosmos was a far more ambitious architect than anyone imagined. Before diving deeper into what Webb's discoveries might mean, it's worth revisiting what scientists actually mean when they talk about the Big Bang. The phrase is so familiar that it often gives the wrong impression. It sounds like an explosion, a blast that sent matter flying outward into empty space. But that's not what happened at all. The Big Bang wasn't an explosion in space, it was an expansion of space. It's the moment when the universe itself began stretching, carrying all matter and energy with it. There was no outside for it to expand into. Space, time, energy, and matter were all created together in that event. According to our best measurements, that expansion began about 13.8 billion years ago. At that time, everything that would one day become galaxies, stars, and planets was compressed into an unimaginably hot, dense state. The early universe was filled with a smooth mixture of energy and particles constantly colliding, annihilating, and forming again. As it expanded, it cooled, and within fractions of a second the fundamental forces separated into the ones we know today: gravity, electromagnetism, and the strong and weak nuclear forces. Those first instants are described by physics with great precision up to a point, but beyond that lies a fog of uncertainty. The earliest moments when the universe was smaller than an atom are governed by physics we don't yet fully understand. A few 100,000 years later, the universe cooled enough for protons and electrons to combine into neutral hydrogen atoms. That made the universe transparent for the first time, allowing light to travel freely. The afterglow of that moment is still visible today as the cosmic microwave background, the faint, uniform radiation that fills the sky in every direction. It's the oldest light we can see directly, a snapshot of the universe when it was only 380,000 years old. Everything beyond that point, the first stars, the first galaxies, the end of the Dark Ages, is inferred from models and indirect evidence. That's exactly the gap Webb was built to explore. The Big Bang theory isn't just a guess, it's supported by a huge range of observations. The cosmic microwave background shows the universe was once hot and dense. The abundance of light elements like hydrogen, helium, and lithium matches what we'd expect if they formed in a rapidly expanding early universe. And the redshift of distant galaxies shows that the universe is still expanding today. Together, these lines of evidence form one of the most successful models in all of science. It explains how the universe went from a smooth sea of particles to a structured cosmos filled with galaxies and stars. So when people say Webb might have found something older than the Big Bang, what they're really challenging isn't the event itself, but the details of what happened afterward. The Big Bang isn't in doubt. The timeline of how fast things developed afterward might be. If Webb's galaxies seem too mature, that could mean our models of star formation, cosmic cooling, or dark matter behaviour need adjusting. It doesn't mean the entire framework collapses. The same thing has happened before in science. When measurements of some stars once seemed to make them older than the universe, scientists didn't throw out the Big Bang. They refined how they measured distances and ages. The paradox vanished once the data improved. Another common misconception is that the Big Bang describes the origin of everything, including why it happened. In truth, it only describes the evolution of the universe from its earliest measurable state. What caused the Big Bang, or what, if anything, came before, is still an open question. Our current laws of physics can't reach that far back. When you run the equations of general relativity backward in time, space and time themselves seem to converge toward a singularity, a point where density and temperature become infinite and the math breaks down. That's not a physical object. It's a signal that our equations stop working there. To go beyond that point, we'll need a theory that unites quantum mechanics and gravity. Many cosmologists think the Big Bang wasn't the literal beginning of everything, but the beginning of the universe as we know it. It may have emerged from a prior state, perhaps a quantum fluctuation, a bounce from a previous cycle, or an event in a larger multiverse. These are fascinating ideas, but they're still speculative. Webb can't directly see that far back, because its instruments detect light, and before the Big Bang there was no light to detect. What it can do is study the conditions of the universe right after the Big Bang, helping us understand what that first moment must have been like. That's why scientists were so surprised by Webb's earliest results. They weren't expecting to find cracks in the Big Bang theory itself. They were expecting to fill in its missing chapters. Instead, the telescope revealed that the first chapters were a lot more dramatic than predicted. The early universe wasn't a quiet nursery of slowly forming stars. It was a cosmic construction zone, building galaxies with unbelievable speed. That discovery doesn't undermine the Big Bang. It makes it even more compelling. It shows that the transition from simplicity to complexity happened faster than we could have imagined. For all its popularity, the phrase "the Big Bang" remains an imperfect label. It was coined by a skeptic, Fred Hoyle, who didn't believe in it. He meant it sarcastically. But the name stuck, and now it represents one of the most well-tested ideas in science. Webb's discoveries are not tearing that idea apart. They're testing its limits, probing the edge of what the theory can currently explain. Every time we find a galaxy that seems too early or too massive, we're not breaking cosmology, we're sharpening it. The Big Bang remains the framework that everything else must fit into, and so far, even the strangest results still do. Understanding this foundation is crucial before we tackle the next question. Where did the older than the Big Bang claim actually come from? And how did such a small scientific anomaly turn into a worldwide story that seemed to rewrite the origin of everything? The phrase "older than the Big Bang" didn't start with a scientist making a bold claim. It started with a misunderstanding that spiraled into a headline. When astronomers first began discussing the early James Webb data, they were shocked by what they saw. Galaxies appearing fully grown only a few 100 million years after the Big Bang. To make sense of this, researchers compared what the models predicted with what the telescope actually measured. In a few cases, the math didn't line up neatly. The light coming from those galaxies suggested that their stars had been shining for longer than the universe was supposed to have existed at that point in time. It was a modelling conflict, not a cosmic impossibility. But that subtlety didn't survive the jump from technical papers to social media feeds. It began when a handful of research teams shared early, unreviewed analyses of Webb's images. They were excited, and for good reason. The telescope was delivering data that challenged the pace of early galaxy formation. One or two papers used phrases like apparent stellar ages, exceeding cosmic age, and observed redshift, meaning the galaxies looked older than the models allowed. To scientists, that's a red flag, a sign that your model might need tweaking. To headline writers, it sounded like a revolution. Within days, online outlets were running dramatic summaries. James Webb finds galaxies older than the universe. Videos and posts amplified it further, turning a technical hiccup into what sounded like proof that the Big Bang had been overturned. The problem is that language in science and language in everyday life don't always match. When scientists say older, they might mean model inconsistent. When readers hear older, they think existed before. Those are very different ideas. In the technical sense, the galaxies weren't older than the Big Bang. They were too evolved for the time in which they were observed. Imagine looking at a photo of a newborn and realising it somehow has the height and vocabulary of a 10-year-old. You wouldn't conclude that the child was born before its parents. You'd realise that something about your assumptions must be wrong. That's exactly how astronomers felt when they saw those early Webb results. As the headlines spread, more confusion followed. Some articles quoted researchers out of context, framing cautious phrases as radical claims. Others blurred the line between metaphor and fact, using the idea of older than time as a hook. It made for great content but poor science. Scientists were quick to clarify that nothing Webb had seen disproved the Big Bang. In fact, the telescope's data depended on the Big Bang model to even calculate those distances. Without the framework of an expanding universe, the idea of looking 13 billion years into the past wouldn't make sense at all. Yet the phrase stuck, partly because it's irresistibly provocative. The idea of something existing before the beginning of everything taps into a deep human curiosity. Even if you know it's just a misunderstanding, you still want to ask, what if? What if the universe isn't a one-time event? What if there was something before? Those questions drive both scientific inquiry and popular imagination. And while Webb hasn't provided evidence for a pre-Big Bang universe, it has reignited interest in that frontier, the place where physics breaks down and philosophy begins. It's also important to remember that this kind of overreaction isn't new. In the 1990s, astronomers using the Hubble Space Telescope ran into a similar issue. They measured the ages of some old stars and found, to their surprise, that those stars appeared older than the universe itself. The solution wasn't to abandon the Big Bang, but to improve the distance measurements and update the Hubble constant, the number describing how fast the universe is expanding. Once the delta became more precise, the paradox vanished. The same pattern is likely playing out now. Webb's early findings are shaking up the details, not the foundation. This misunderstanding also reveals something about how science and media interact today. Scientists communicate with equations and error bars. The public engages through emotion and story. When those two worlds meet, nuance often gets lost. A phrase meant to signal uncertainty can be mistaken for a discovery. But in a way, that's also what makes astronomy so engaging. People care about the story of where we came from, and they want to understand it in human terms. Even when headlines get it wrong, they are a sign that people are paying attention. Behind the hype, the real story is actually more interesting. Webb didn't find something older than the Big Bang. It found evidence that the early universe might have been capable of forming stars and galaxies much faster than expected. That discovery could mean our understanding of physics during the universe's first few 100 million years is incomplete. Maybe dark matter played a bigger role. Maybe the first stars formed differently. Or maybe our instruments are just starting to show us the fine print of cosmic history. Whatever the case, the data are forcing cosmologists to revisit how the first structures took shape, which is far more exciting than a sensational claim about breaking the laws of time. So the phrase older than the Big Bang survives online, even though it's not literally true, because it captures that feeling of disorientation that real discovery often brings. Science rarely works in neat final statements. It moves through confusion, correction, and refinement. Webb's data are right in the middle of that process. Messy, challenging, and full of potential. What began as a headline might actually end up reshaping our understanding of how fast the cosmos learned to build itself. And that brings us to the deeper mystery. If nothing Webb has seen truly predates the Big Bang, then what would it mean for something to exist before it? What do scientists even mean when they talk about before, a moment when time itself begins? When the first round of Webb data reached Earth, it didn't arrive as a single eureka image, but as a flood of numbers. Every exposure contained millions of light measurements, each one representing photons that had been travelling across the cosmos since the dawn of time. Among those early results, astronomers noticed a handful of extremely faint red dots that didn't fit expectations. They weren't the fuzzy, primitive blobs scientists thought they'd find. They were compact, luminous and far away, so far that their light had been stretched by the expansion of the universe more than any other object ever seen. One of these faint spots in particular stood out. It wasn't just distant, it was unexpectedly bright. When researchers calculated its redshift, the number that tells how far its light has travelled, the result pointed to a time less than 300 million years after the Big Bang. To put that in perspective, if the universe were a 24-hour day, this galaxy would have formed in the first 5 minutes. That was astonishing on its own, but what made it even stranger was what the light seemed to reveal about its contents. Its colour suggested the presence of heavier elements, things like carbon and oxygen, that require multiple generations of stars to exist. In other words, this galaxy looked like it had already lived a long, busy life in a universe that had barely started. At first, the astronomy community reacted with healthy skepticism. It's standard practice to treat extreme results with caution, especially when they challenge established theory. The data came from what's called photometric redshift, which uses the color of the light to estimate distance. That method is useful, but it can be fooled by dust, unusual star types, or overlapping sources. The only way to confirm the result was through spectroscopy, splitting the light into precise wavelengths to identify its chemical fingerprints. When those follow-up measurements arrived months later, the distance held up. The galaxy really was that far away. That was the moment the firestorm began. The finding sent shockwaves through the research community because it forced scientists to confront how such a galaxy could have appeared so quickly. According to the models, there simply hadn't been enough time since the Big Bang for so many stars to form, die, and enrich the surrounding gas with heavier elements. Star formation is a chain reaction. The first generation of stars, massive and short-lived, explode and seed the next. That process takes hundreds of millions of years to produce measurable amounts of heavier elements. Yet this galaxy showed signs of them already. That meant either the first generation of stars formed almost immediately after the Big Bang, or the process of enrichment was far more efficient than anyone realized. The excitement wasn't limited to one discovery. As Webb kept observing, more galaxies with similar characteristics appeared. They seemed to cluster in a narrow window of time, each one representing a snapshot of the universe's frantic, early activity. The pattern was impossible to ignore. The early cosmos was building galaxies at breakneck speed. For astronomers who had spent decades refining models of slow, steady growth, it was like discovering that the universe had sprinted through its infancy. This single galaxy and its companions forced a new wave of questions. Were the instruments truly capturing what they seemed to? Could faint foreground objects be contaminating the signal? Was there some unknown physical process amplifying the light? Every answer led to new complications. The instruments were performing perfectly. The data were consistent. The only things left to question were the assumptions baked into the models themselves. If galaxies could reach this level of maturity so soon after the Big Bang, it meant the seeds of structure had to form much earlier than thought. The first clumps of matter might have condensed only tens of millions of years after the Big Bang, almost instantly, by cosmic standards. That would change the entire timeline of reionization, the period when the first stars and galaxies ionized the hydrogen gas that filled the universe, allowing light to travel freely again. The early universe wasn't a tranquil void. It was a glowing, turbulent landscape where gravity, radiation, and matter interacted in ways we're only beginning to understand. The discovery also had ripple effects beyond galaxy formation. It raised questions about the rate at which the universe expands. If these galaxies existed earlier than expected, could our estimate of the universe's age be slightly off? Could the so-called Hubble tension, the small but persistent disagreement between different methods of measuring the expansion rate, be connected to this? These are open questions, and Webb's data might hold the clues. For many researchers, the thrill of this discovery wasn't in proving something wrong, but in uncovering something unexpected. That's how science moves forward. The telescope had done exactly what it was designed to do: show us something we didn't anticipate. It revealed that our cosmic timeline might need editing, not erasing. The Big Bang still stands as the beginning of space and time, but the path from that moment to the first galaxies is now full of twists we didn't see coming. For the public, though, nuance is often the first thing lost in translation. The moment those early findings were announced, the internet latched onto the wildest interpretation. Webb has found something older than the Big Bang. The truth was subtler and, in many ways, more profound. Webb had revealed that the universe wasted no time creating order out of chaos. It showed that within a few 100 million years, gravity was already shaping matter into galaxies, lighting up the darkness and setting the stage for everything that would follow. That's the power of this one observation. It didn't rewrite the beginning of the universe, it rewrote how fast that beginning became complex. What scientists now want to know is how that happened. What physical forces or early conditions could have made galaxies grow up so quickly? Was it the influence of dark matter, the behaviour of the first stars? Or could it point to a missing ingredient in our understanding of cosmic evolution? Those questions became the foundation for a new generation of research. Webb had done more than photograph ancient light. It had set off a debate about how the first structures in the universe formed and what that means for the physics of the early cosmos. And that debate leads directly to the next question scientists had to face. How exactly do they figure out how old these galaxies are in the first place? When astronomers talk about a galaxy being 13 billion years old, or formed 300 million years after the Big Bang, they're not pulling those numbers out of thin air. They're extracting them from light, the only messenger that can cross billions of years to reach us. Every speck of light Webb collects contains a record of where it's been and what it's passed through. Decoding that record is how scientists reconstruct the age of the cosmos. But the process is delicate, full of assumptions, and sensitive to even the smallest error. Understanding how it works explains why phrases like older than the Big Bang can appear in the first place. The first step is measuring distance, and the tool for that is redshift. When light travels through an expanding universe, its wavelength stretches, just as a siren sounds lower in pitch when an ambulance speeds away. The farther the light travels, the more it stretches. By comparing how much a known spectral line has shifted, astronomers can calculate exactly how far the light has travelled, and therefore how long ago it left its source. That number is converted into cosmic time using the standard cosmological model, which tells us how the universe's expansion rate has changed over billions of years. A redshift of 1 means the light has been stretched so that the universe is now twice as big as when that light left. A redshift of 10 means it's 11 times larger. The most distant galaxies Webb has measured are around redshift 13 to 14, incredibly close to the universe's beginning. Once the distance is known, the next step is figuring out how old the galaxy's stars are. This is where things get complicated. When starlight reaches Webb's instruments, it's not a uniform colour. It's a blend of different wavelengths produced by millions of stars at various stages of life. By analysing the overall shape of that spectrum, scientists can estimate the ages of the stars inside. Younger galaxies shine with bluer light because they're dominated by hot, massive stars that burn quickly. Older galaxies look redder because most of their hot stars have already died, leaving cooler, longer-lived ones behind. But that rule has exceptions. Dust, for example, can make a galaxy look redder than it really is by scattering and absorbing blue light. That's one of the biggest sources of confusion in interpreting early universe data. To deal with this, astronomers use computer models called stellar population synthesis. These models combine physics, chemistry, and statistics to predict what a galaxy's light should look like at different ages and compositions. Scientists adjust the parameters, star formation rates, metallicity, dust content, and so on, until the model matches what Webb observes. The best fit model gives an estimate for how old the stars are and how quickly the galaxy formed them. But best fit doesn't mean certain. Many combinations can reproduce similar light curves. If the assumptions baked into the model are off, the inferred ages can be misleading. That's how some of Webb's earliest results produced galaxies that seem to contain stars older than the universe at that time. The models were built using data from closer, more mature galaxies, not from the extreme conditions of the early universe. They assumed familiar patterns of star formation, but the first generations of stars were likely very different, larger, hotter, and shorter-lived. If the models don't account for that, they can interpret the light as coming from an older, more evolved population than it really is. It's like using the growth chart of a modern child to estimate the age of a prehistoric one. You'd get the wrong number because the conditions were different. Another challenge lies in the telescope's sensitivity. Webb is so powerful that it can detect faint traces of light from galaxies that are barely formed. But that faintness also means small errors in brightness or colour can translate into big uncertainties in age. Add in the effects of cosmic dust, gravitational lensing, and instrumental noise, and the margin for error can grow. Astronomers often have to work with incomplete data, especially when a galaxy is so distant that Webb can detect only a few key wavelengths. That leaves room for interpretation, and sometimes overinterpretation. The goal then is to move from photometric estimates, which are quick but rough, to spectroscopic ones, which are slower but precise. Spectroscopy splits light into its component wavelengths, revealing a barcode-like pattern of absorption and emission lines. Each element and molecule leaves its own signature, so by studying these lines, astronomers can tell not only what a galaxy is made of, but how old its stars are and how much gas and dust it contains. This is how Webb confirmed that some of those early galaxies really are as distant as they seemed. Their spectra showed clear signs of hydrogen, and other elements shifted far into the infrared, proof that their light had been stretched for over 13 billion years. Still, even spectroscopy has limits. At extreme distances, the light is so faint that only a few lines can be measured, and those lines can be blurred or distorted by intervening material. To get around this, scientists combine Webb's data with results from other observatories, radio telescopes, X-ray instruments, and computer simulations that model galaxy formation under different conditions. Piece by piece, they build a more complete picture. The beauty of this process is that it turns something as intangible as starlight into a cosmic clock. Every wavelength carries timing information. The bluer the light, the younger the stars. The redder, the older. And by studying entire populations of galaxies at different distances, astronomers can map how star formation evolved over time. It's like flipping through a photo album of the universe's childhood, except each photo was taken billions of years apart. This is also why the claims about something being older than the Big Bang don't hold up under scrutiny. What's really happening is that our methods of estimating age are colliding with the limits of our assumptions. The data are solid, the galaxies are real, and they are incredibly ancient. But the models we use to translate light into time might need a tune-up. Webb isn't disproving the Big Bang, it's helping us refine our cosmic clock. Every new observation adds a data point that sharpens that timeline. In the long run, these refinements are what makes science self-correcting. The same process that created the confusion will eventually resolve it. As more galaxies are observed, as more spectra are collected, and as models adjust to match the extreme conditions of the early universe, those impossible ages will likely fall back into place. The mystery isn't a failure of cosmology, it's evidence that we're finally looking close enough to find its edges. For now, what's clear is that Webb has pushed the art of cosmic dating to its limits. It's showing us that the early universe was not a slow, patient builder, but an overachiever, one that learned to form stars and galaxies almost immediately. And while that may seem like a problem for our models, it's also a sign that we're finally seeing the universe for what it really was: fast, chaotic, and astonishingly creative right from the start. When scientists talk about an age crisis in cosmology, they don't mean the universe is having an existential breakdown. It's a shorthand for when the math doesn't quite add up. That's exactly what started happening after Webb's first few months of observations. The telescope began finding galaxies that, according to existing models, seemed to contain stars older than the universe was supposed to be at that moment in cosmic history. It was like opening a history book and finding a detailed chapter about cities that supposedly existed before civilization began. The data didn't fit the timeline. To see why that's a problem, remember that in the standard model, time begins with the Big Bang. Everything that exists, space, matter, energy, and even the flow of time itself, comes out of that starting point. When we look at galaxies that formed a few 100 million years later, we expect them to be young, chaotic, and relatively small. But Webb revealed some that looked well organized and chemically evolved, containing stars that appeared to have been burning for hundreds of millions of years already. If those age estimates were right, it meant these stars somehow started forming before the universe itself was old enough to allow for it. That's the essence of the age crisis. At first glance, it sounds like a fatal blow to the Big Bang, but the crisis isn't really about the event itself. It's about how we interpret the evidence that follows. The Big Bang theory describes the expansion and evolution of the universe, and it's supported by multiple independent lines of data: the cosmic microwave background, the distribution of galaxies, and the abundance of light elements. Those foundations are solid. What's in question is how we estimate the ages of specific galaxies and how fast structure formed afterward. It's not a problem with the Big Bang, it's a problem with our clocks. Part of the confusion comes from how star ages are calculated. Astronomers use models that link a star's brightness and colour to its age and chemical makeup. But those models are based on stars in the nearby universe, ones that formed billions of years after the Big Bang, under very different conditions. The first generation of stars, born in a universe still cooling from its creation, were likely far more massive and short-lived. Their light would dominate a galaxy's colour and make it appear older in the models than it actually is. In other words, we might be mistaking the vigour of youth for the glow of age. Another piece of the puzzle involves how galaxies build up over time. Traditional models assume a gradual process. Small clumps of matter merge, stars form, and over hundreds of millions of years, galaxies grow. But Webb's discoveries suggest that this process was much faster in the early universe. High-density regions rich in dark matter could have collapsed more quickly than expected, triggering intense bursts of star formation. If that's the case, then galaxies could reach a mature state in a fraction of the time our old models allowed. What looked like an age crisis might just be evidence that the early universe worked on fast forward. There's also the role of heavy elements to consider. In astronomy, metals means anything heavier than helium, elements created in the cores of stars and spread through space by supernova explosions. The more metals a galaxy contains, the more previous generations of stars it must have had. Webb's detection of metals in very early galaxies was surprising, but not necessarily impossible. Massive first-generation stars could have lived and died in just a few million years, producing heavy elements quickly. That would make their galaxies appear chemically old, even though they were still young by cosmic standards. So the age crisis may not be a sign that the Big Bang's wrong, but that it's incomplete in the details. Our current simulations of the early universe, while powerful, still rely on assumptions about how gas cools, how stars ignite, and how feedback from supernova affects future generations. Webb is showing us that those assumptions need updating. The early cosmos might have been more efficient at forming stars, more turbulent and more compact than we thought. This kind of mismatch between theory and observation has happened before. In the 1990s, astronomers thought they'd found stars in the Milky Way that were older than the universe itself. It was a real age crisis at the time, and it sounded just as dramatic. The solution turned out to be a mix of better distance measurements, improved models of stellar evolution, and a refined value for the universe's expansion rate. Once those numbers were corrected, the paradox vanished. What seemed like a contradiction became a calibration issue. Webb's findings might follow the same pattern. Still, the current age tension is scientifically exciting because it pushes models into untested territory. If galaxies really formed faster than expected, we'll need to understand what allowed that to happen. Was dark matter clumping differently than our simulations suggest? Were the first stars so massive and energetic that they lit up the universe almost instantly? Or are we seeing something entirely new? An early phase of structure formation we didn't even know existed. Each of those possibilities carries implications for how we understand not just the first galaxies, but the evolution of everything that came after. The important takeaway is that older than the Big Bang is not a literal claim, it's a symptom of the models being pushed to their limits. Every time our instruments get better, the universe tests our confidence in our theories. That's the pattern of discovery. Data surprises us, we adjust, and the picture becomes sharper. The Big Bang remains the starting point, but the timeline that follows is getting more detailed, more complex, more dynamic, and more human in its process of revision. For the first time, Webb is giving us a front-row seat to how galaxies really took shape, not as we imagined them in equations, but as they actually were. Wild, uneven, and full of surprises. The so-called age crisis isn't a breaking point in cosmology. It's a clue that we're finally seeing the universe in its raw, untamed youth. And that raises a deeper question. If nothing Webb has seen truly predates the Big Bang, could there still be something beyond it? Something that existed before time, or outside it entirely? Scientists have begun to explore that possibility, and their theories take us right to the edge of what physics can currently describe. If the idea of something existing before the Big Bang sounds confusing, that's because it challenges how physics defines time itself. Our sense of before and after depends on time moving in one direction. But according to modern cosmology, time as we experience it only began when the universe began expanding. Before that, the concepts of earlier and later simply didn't apply. That's not just philosophy, it's a mathematical boundary baked into the equations that describe the universe. Einstein's general theory of relativity treats space and time as part of a single fabric, space-time. It bends and stretches under the influence of matter and energy. When cosmologists trace the expansion of the universe backward through those equations, the distances between all points in space shrink, and the temperature and density rise. Eventually, they reach a point where the equations predict infinite density, a singularity. At that point, the math stops working. It's not that the universe physically turned into a pinhead of infinite energy. It's that our current theories can't describe what happens under such extreme conditions. The singularity marks the edge of our knowledge. What happens at or beyond that edge is the domain of theoretical physics. One of the main contenders to go past it is quantum gravity, a still developing framework that tries to unite the smooth space-time of relativity with the probabilistic world of quantum mechanics. In quantum theory, nothing is perfectly defined. Everything fluctuates. If space-time itself has a quantum nature, then at incredibly small scales, it might foam with energy, constantly fluctuating rather than collapsing into a singular point. In that picture, the Big Bang wasn't a beginning from nothing but a phase transition, a shift from a quantum state of space-time into the classical universe we live in now. To get a sense of scale, physicists use something called the Planck time, about 10 to the negative 43 seconds after the Big Bang. That's the earliest moment where our physics can still make sense. Before that, literally within a tiny fraction of a trillionth of a second, everything breaks down. Temperatures and densities were so high that gravity itself might have behaved differently. Quantum fluctuations of space and time could have created tiny, short-lived universes, most collapsing immediately, with one, ours, continuing to expand. It's a mind-bending scenario, but it's mathematically plausible. The idea of a before time often comes up in models where the universe doesn't start from a singularity, but from a bounce. In those cyclic or big bounce cosmologies, the universe expands, slows, contracts, and then bounces back into expansion again. Each cycle erases most of the information from the one before it, leaving only subtle imprints. This could, in theory, explain why the cosmic microwave background, the leftover radiation from the Big Bang, is so smooth. In these models, the Big Bang isn't the creation of time, it's the latest renewal of it. Other theories take an even stranger route. Some propose that time itself may have emerged gradually. In these frameworks, the universe started as a timeless quantum system, described only by probabilities. As it expanded and cooled, classical time crystallized out of that quantum haze. In other words, the arrow of time, the sense of past to future, could be a property that appeared when the universe reached a certain level of order. If that's true, then before the Big Bang might have been a state without cause or sequence, something fundamentally beyond our intuition. Inflation theory, which describes a burst of rapid expansion just after the Big Bang, also connects to these questions. Inflation helps explain why the universe looks uniform on large scales and why space is nearly flat. But it raises new puzzles. What started inflation and what stopped it? Some versions suggest inflation never completely ends. It continues in other regions of space-time, endlessly spawning new universes. That idea, called eternal inflation, would make the Big Bang just one of many beginnings scattered through an infinite cosmic landscape. From our perspective, that's the beginning of our time, but elsewhere other timelines might have started long before, or might not have begun yet at all. At this point, the line between physics and philosophy gets thin. Even the most sophisticated equations can only go so far without direct evidence. Webb's mission doesn't extend into the realm before time, but its observations could constrain these theories by showing how early the first structures appeared and what physical laws dominated those moments. For instance, if we discover that gravity behaved differently at extremely high energies, or that the distribution of early galaxies deviates from what inflation predicts, we might infer something about what happened before the universe became transparent to light. It's also worth remembering that science has faced similar conceptual boundaries before. There was a time when the idea of atoms was philosophical guesswork, when relativity seemed to contradict common sense, and when quantum mechanics was dismissed as nonsense. Each time, new evidence forced a shift in how we define what's possible. The physics of before time may one day move from speculation to testable theory the same way. Gravitational wave observatories and next-generation telescopes could detect signals imprinted by the earliest cosmic processes, ripples or distortions left over from those first fractions of a second. If we ever find those, they might offer a glimpse into whatever existed just before time itself began ticking. For now, though, the Big Bang remains our earliest readable chapter. Webb's discoveries haven't reached past it, but they are rewriting what we know about what came right after. They're revealing that the moment space and time began wasn't followed by a quiet dawn, but by an immediate and astonishing burst of creativity. The universe didn't ease into existence. It erupted into complexity almost as soon as it could. That realization shifts the focus from what came before to how fast things happened after. Because if galaxies, stars, and black holes appeared faster than our physics allows, something fundamental about those first moments, perhaps the very laws of nature themselves, might need revisiting. The most important thing to understand about James Webb's discoveries is that they don't overturn the Big Bang. They refine it. What Webb has done is reveal a universe that evolved far more quickly and energetically than anyone expected. The telescope isn't showing us that our cosmic origin story was wrong. It's showing us that the opening chapters were much denser, brighter, and busier than we imagined. This is how science grows stronger. When new observations push existing models to their limits and force us to improve them. Before Webb, our best picture of the early universe came from simulations and older telescopes like Hubble. Those observations showed young galaxies as dim, irregular, and chaotic, small pockets of light scattered in the dark. Theoretical models predicted that it would take hundreds of millions of years for matter to organize itself into large, bright systems. Webb shattered that assumption almost immediately. Its first deep-field images revealed galaxies that appeared massive and well-structured within just a few 100 million years of the Big Bang. That discovery creates a problem only if we assume our previous models were complete. But they weren't. Cosmology is built on approximations. Simulations of galaxy formation depend on parameters like the density of dark matter, the behavior of gas under extreme pressure, and the rate at which stars form and explode. Many of those factors are based on conditions in the later universe, not the earliest one. Webb's data are forcing scientists to revisit those assumptions and test how physics behaves when the universe is only a fraction of its current age. For example, one of the biggest surprises involves star formation rates. Galaxies in the early universe seem to have been producing stars much faster than expected, sometimes 100 times the rate of similar galaxies today. That's not supposed to happen so soon after the Big Bang, because the gas was still hot and diffuse. To form stars efficiently, gas must cool and clump under gravity. But Webb's images show that somehow those conditions were achieved almost instantly. This could mean that the first regions of dark matter created deep gravitational wells that pulled gas together faster, or that the first stars emitted radiation that helped trigger further collapse. Either way, it implies that the young cosmos was a more efficient star factory than our models allow. Another area where Webb is reshaping understanding is the chemical evolution of the universe. When scientists analysed the light from these ancient galaxies, they found traces of heavier elements, carbon, oxygen, and even hints of complex molecules. In the standard timeline, these elements shouldn't exist in large quantities that early. They're made in the cores of massive stars and scattered by supernova explosions. For there to be so much of them, the first stars must have lived and died extraordinarily quickly, enriching the gas around them in record time. That forces scientists to rethink the life cycles of the earliest stars. They may have been much larger and hotter than today's, burning through their fuel in just a few million years, and leaving behind black holes that helped shape the first galaxies. Webb is also raising new questions about black holes themselves. Some of the galaxies it has detected seem to host central black holes with masses millions of times greater than the Sun. Under normal conditions, it would take billions of years for a black hole to grow that big. So how could they exist when the universe was only a few 100 million years old? One possibility is that black holes in the early universe didn't start small. Instead of forming from dying stars, they may have collapsed directly from dense clouds of gas, a shortcut that skips the slow build-up phase entirely. If that's true, these direct collapse black holes could explain how the earliest galaxies formed around massive centres of gravity so quickly. Then there's the issue of brightness. Some of Webb's galaxies are so luminous that they strain the limits of what physics predicts. At first, scientists wondered if gravitational lensing, where a closer galaxy bends and magnifies light from a more distant one, was making them appear brighter. In some cases, that turned out to be true, but not for all. A growing number of these objects seem to be genuinely bright, suggesting that they're forming stars at an astonishing pace, or that they contain phenomena we don't yet understand. These outliers push astrophysicists to refine their theories of radiation, feedback, and energy balance in the early cosmos. All of this points to one clear conclusion. Our models underestimated the efficiency of the early universe. The cosmic ingredients were the same: gravity, gas, dark matter, but the recipe produced results much faster than expected. That doesn't challenge the Big Bang itself. It challenges the fine print of how structure forms within it. Just as early climate models struggled until they accounted for feedback loops and hidden variables, cosmology is now updating its own equations to capture the feedback between dark matter, radiation, and star formation. The beauty of this process is that it doesn't replace old science, it strengthens it. The Big Bang model has always been flexible. It doesn't prescribe how fast galaxies should form. It only sets the initial conditions and the laws of physics that govern what follows. When new data come in, we adjust those parameters. That's what's happening now. Webb's discoveries are not a crisis, they're a calibration. This refinement extends to our understanding of cosmic inflation and dark matter, two cornerstones of modern cosmology. Inflation theory predicts that the universe expanded exponentially just after the Big Bang, smoothing out irregularities and creating the seeds for all future structure. Webb's detailed look at the earliest galaxies helps test those predictions by showing how those seeds grew. If we find more structure at earlier times than inflation predicts, it might mean the inflationary process was more complex or lasted longer than we thought. Similarly, the clustering of galaxies in Webb's data helps map how dark matter is distributed. If it turns out that dark matter clumps more tightly than expected, that could explain why galaxies formed so quickly, and could even hint at the true nature of dark matter itself. In this sense, Webb is not breaking cosmology, it's giving it higher resolution. Just as microscopes revolutionized biology by revealing details invisible to the naked eye, Webb is doing the same for cosmic history. It's not telling us the Big Bang was wrong, it's showing us how incomplete our picture was. The pace at which these refinements are happening is unprecedented. Within just a couple of years, Webb has already forced revisions to several textbooks and simulations. Entire research fields, like early star formation, ionization, and galaxy assembly, are being rewritten. It's a rare moment in science when technology advances so far that it instantly outpaces theory. But that's exactly what makes this era exciting. The key takeaway is simple but profound. The Big Bang remains the framework of cosmology, but the story that follows it has become far richer. The universe wasn't a slow learner, it was an overachiever. The first stars, galaxies, and black holes appeared in a cosmic rush, challenging our expectations of how fast complexity can emerge. Webb's discoveries don't contradict the Big Bang, they celebrate it by showing us just how fertile its aftermath really was. And that brings up a question that's even more intriguing than what came before the Big Bang. If the universe was able to form galaxies so quickly, what was driving that efficiency? What unseen forces or hidden ingredients made the early cosmos so productive? To answer that, scientists have to look deeper into the invisible backbone of the universe, the mysterious scaffolding of dark matter and the rivers of gas that fed those first bursts of light. To understand how the universe could have built complex structures so quickly, we need to look beyond what telescopes can see. The visible parts of galaxies, the stars, the gas, the glowing dust, are only the surface of a much deeper framework. Beneath it all lies a vast invisible skeleton made of dark matter. This unseen component doesn't emit or absorb light, but its gravity shapes everything we observe. Without it, galaxies would never have formed at all. And Webb's discoveries are now pushing scientists to rethink exactly how dark matter behaved in those first few 100 million years. In the standard model, dark matter makes up roughly 85% of the universe's total mass. It interacts with normal matter primarily through gravity, forming huge clumps that act as gravitational wells. These wells are where ordinary gas, mostly hydrogen and helium from the Big Bang, collects and cools to form stars. Think of dark matter as the scaffolding of the cosmos, invisible beams and supports around which everything else takes shape. When the universe was young, tiny variations in density caused dark matter to clump unevenly. Over time, those clumps grew through gravity, merging into larger and larger halos. Eventually, these halos became the gravitational anchors of galaxies. But Webb's data suggests that this process may have been even faster and more efficient than simulations predicted. The galaxies it sees at high redshift, those ancient compact systems, imply that dark matter halos must have pulled together far more quickly than our models allow. If dark matter behaved differently in the early universe, that could explain why stars and galaxies appeared so soon. Some physicists proposed that dark matter particles might interact with each other more strongly than previously thought, a concept known as self-interacting dark matter. This would allow dark matter to form denser cores, speeding up the collapse of gas clouds and igniting star formation earlier. Another factor could be the cooling efficiency of the primordial gas. For stars to form, hydrogen and helium need to shed heat so they can condense under gravity. In the modern universe, that cooling's aided by metals, atoms heavier than helium that radiate energy away. But in the beginning, there were no metals. So how did the first gas clouds cool enough to form stars? Astronomers think that molecular hydrogen, even though it's rare and fragile, acted as the key coolant. These molecules allowed pockets of gas to lose energy and collapse. Webb's infrared instruments can detect the faint signatures of molecular hydrogen in ancient galaxies, giving scientists a direct way to test how that process unfolded. The interplay between dark matter and gas isn't one-sided. As soon as stars begin to form, they start pushing back against their environment. The first supernovae release powerful bursts of energy that heat nearby gas and can even blow it out of a young galaxy. At the same time, gravity pulls fresh material back in, feeding new rounds of star formation. This tug-of-war shapes the growth of galaxies over time. Webb's detailed view of early systems is helping astronomers see that process in action. Many of the galaxies it observes are incredibly compact, suggesting that gas was funneled into their centres with extraordinary efficiency. That could mean the dark matter halos guiding them were unusually dense, with gravity strong enough to counteract the explosions of newborn stars. There's also evidence that dark matter might have influenced not just how galaxies formed, but how they interacted. In a dense early universe, halos would have been close together, merging frequently. Each merger would have triggered a burst of star formation as gas clouds collided and compressed. Webb has caught glimpses of such interactions, even at very high redshift, tiny, overlapping smudges of light that may be galaxies in the process of colliding. These cosmic mergers could explain how galaxies grew so massive so quickly. They weren't building in isolation, but through constant cooperation and collision. Beyond that, dark matter may also help explain the formation of the first black holes. If certain dark matter halos were especially compact, their gravitational pull could have drawn gas inward so fast that it skipped the normal process of star formation altogether. Instead of forming stars first and black holes later, some regions might have collapsed directly into massive black holes right away. Those black holes, in turn, would have influenced the growth of their host galaxies, pulling in gas, igniting jets of radiation, and shaping the surrounding environment. This kind of feedback loop could account for why Webb sees galaxies that already appear to host massive central black holes at such an early time. The more we learn about these interactions, the clearer it becomes that dark matter was the architect of cosmic structure. Without it, the early universe would have remained a diffuse fog. With it, the fog condensed into a web of galaxies connected by filaments of gas. That web still exists today. Every galaxy, including our own Milky Way, sits at the intersection of these filaments, bound together by dark matter's invisible gravity. Webb's ability to peer into the earliest stages of that network is giving us our first direct glimpse of how the cosmic web came alive. Still, the exact nature of dark matter remains one of science's greatest mysteries. We can map its influence, but we don't know what it is made of. The leading idea is that it consists of exotic particles that barely interact with normal matter. But Webb's results may force physicists to consider alternatives. If dark matter clumped differently in the early universe than it does today, maybe its properties aren't constant. Perhaps it behaves one way when it's cold and another when it's hot. Or maybe there are multiple kinds of dark matter with different masses and interaction strengths. These questions stretch beyond astronomy into the realm of particle physics, where scientists are searching for dark matter candidates in underground detectors and particle colliders. Then there's the role of gas itself, the visible half of the story. The early universe was dominated by hydrogen, with helium as a close second. These gases filled the expanding space like a thin mist, drawn into dark matter halos by gravity. Over time, the densest regions ignited into stars, while ultraviolet light from those stars ionized the surrounding gas, creating the era known as rayonization. Webb's deep field observations are capturing this process in detail, showing patches of ionized and neutral hydrogen coexisting in a cosmic patchwork. This is where the universe transformed from opaque to transparent. And understanding that transition is one of Webb's key missions. Together, dark matter and gas tell a story of cooperation on a cosmic scale. One provides the invisible framework, the other fills it with light. Webb's discoveries are revealing that this partnership started earlier and worked faster than we thought. Instead of a slow, hesitant dawn, the universe's first few 100 million years were an explosive construction project driven by invisible gravity and rivers of gas. The result was a universe already teeming with galaxies before the first billion years had passed. These insights are now guiding the next phase of research. Scientists are updating simulations to see what happens if dark matter clumps more tightly or if early gas cools more efficiently. Each new Webb observation acts as a test for those models, helping to narrow down which combinations of physics reproduce what we actually see. So far, the message is clear. The early universe was a place of extremes: dense, hot, turbulent, and astonishingly creative. And just as dark matter provided the skeleton for galaxies, these discoveries are giving structure to something else: a new understanding of how cosmic history really began. But the surprises don't end there. Some of the galaxies Webb has captured appear so big, bright, and massive that even with dark matter and fast gas cooling, they remain difficult to explain. These are the systems scientists now call too massive, too soon, and they are at the heart of one of the biggest debates in modern cosmology. The phrase too massive, too soon has become one of the defining soundbites of the Webb era. It captures the shock and confusion that swept through the scientific community when astronomers began analysing the telescope's earliest data. Some of the galaxies Webb detected in its first deep field images appeared to contain as much mass as our Milky Way, even though they existed when the universe was barely a few 100 million years old. According to every established model, galaxies that large simply shouldn't have had enough time to form. They weren't supposed to exist yet. Before Webb, most astronomers believed galaxy formation was a slow and gradual process. The first galaxies were thought to start small, with only a few million stars, and then grow over billions of years through mergers and accretion. Simulations suggested that it would take at least 1 billion years for a galaxy to reach the size of the Milky Way. Yet Webb's infrared eyes, peering back to a time when the universe was less than 3% of its current age, were revealing galaxies that looked fully grown. They had the brightness, the density, and in some cases even the structure of mature systems. The discovery was so unexpected that it set off a wave of reanalysis, debate, and skepticism across the field. The first question everyone asked was the simplest one: could the measurements be wrong? It wouldn't be the first time that early data pushed instruments to their limits. When Webb's team released its initial observations, they were based on photometric redshifts, distance estimates derived from the colours of the galaxy's light. It's a proven method, but not infallible. Dust, overlapping sources, or unusual star populations can distort a galaxy's colour and trick astronomers into thinking it's farther away, and therefore older than it really is. Some researchers suspected that these galaxies weren't actually as ancient as they seemed, and that once spectroscopic data came in, their redshifts would drop. In a few cases, that's exactly what happened. Some candidates turned out to be closer than originally thought, but others held their ground. Follow-up spectroscopy confirmed that several of these impossible galaxies really were as distant and as luminous as first reported. That forced scientists to confront the harder question: if the distances were right, how could galaxies this massive exist so early? One possibility was that their brightness was being exaggerated by gravitational lensing. If a closer galaxy or cluster sat along the line of sight, its gravity could bend and magnify the light of a more distant one, making it look bigger and brighter. Webb's sharp vision, however, is good enough to detect lensing effects, and many of the too massive galaxies showed none. Their light appeared to be coming from compact, undistorted sources. That made the situation even stranger. Another potential explanation was that the models of stellar populations were off. The galaxies might not actually be as massive as they appeared. They could simply be forming stars at an extreme rate. A galaxy that's furiously producing new, hot stars will shine very brightly without necessarily containing a huge amount of mass. It's like mistaking a burst of fireworks for a permanent city of lights. But even this adjustment couldn't fully solve the problem. Some of these galaxies were so luminous that even assuming the most extreme star formation rates, their implied masses remained enormous. The implications were serious. If these galaxies were truly as large and old as they appeared, it would mean that the universe built massive structures far faster than our models allow. That would require rethinking the physics of early star formation, gas cooling, and dark matter clustering. It could even hint at new types of matter or interactions that made the early cosmos more efficient at turning gas into stars. But before declaring a revolution, scientists did what scientists always do. They looked for more data. As more Webb observations rolled in, a more nuanced picture began to emerge. Not every early galaxy was a monster. The universe at those times was full of small, chaotic systems too, just as theory predicted. The two massive galaxies might represent the extreme tail of the distribution, the cosmic overachievers that formed in unusually dense regions where matter was concentrated. In the language of statistics, they were outliers, but not necessarily rule breakers. If the early universe was slightly clumpier than expected, those regions could have formed large galaxies quickly, while the rest of space developed more slowly. Still, the sheer number of these massive early galaxies remains hard to explain. Webb has found more of them than models predicted, even after accounting for observational biases. That suggests the early universe was not only efficient at building galaxies, but also prolific. Gravity seemed to be working overtime, pulling gas and dark matter together with extraordinary speed. Some simulations now incorporate stronger feedback loops, faster cooling rates, or alternative dark matter scenarios to reproduce what Webb is seeing. These adjustments don't destroy the Big Bang framework, they refine it, filling in the messy details that were previously invisible. The debate over these galaxies has also revived old questions about the expansion rate of the universe. If the cosmos expanded slightly slower in its earlier stages than we think, that would give more time for large structures to form. Conversely, if it expanded faster later on, that could help explain the current Hubble tension, the mismatch between different measurements of cosmic expansion today. Webb's data could help bridge those two puzzles by providing a more detailed timeline of how structure growth and expansion interacted over time. There's another more exotic possibility that some researchers are exploring, that we might be seeing hints of new physics operating in the early universe. Perhaps dark matter behaved differently back then, interacting with radiation or itself in ways that made galaxies form faster. Or maybe there's an unknown field or particle that accelerated early growth. These ideas are speculative, but that's how breakthroughs often begin, with a result that doesn't quite fit. Whatever the explanation turns out to be, the too massive, too soon problem illustrates how science really works. It's not about defending old theories at all costs or chasing sensational claims. It's about letting the evidence reshape our understanding. Webb hasn't disproved the Big Bang. It's doing something far more interesting. It's revealing where our story of the universe is incomplete. The telescope is like a spotlight sweeping across a stage, illuminating details the audience couldn't see before. Now that those details are visible, it's up to theorists to rewrite the script. These massive galaxies are the universe's way of reminding us that it's always a step ahead of our expectations. They force us to question our assumptions about how quickly order can arise from chaos. And in doing so, they bring us closer to a deeper truth, that the cosmos is not just expanding in space, but in our understanding of it. The debate is far from over. More Webb observations are on the way, and with them more opportunities to test these ideas. But one thing is clear. The early universe was a far more ambitious architect than we gave it credit for. And the story of those impossibly massive galaxies is still unfolding, leading directly into the next chapter of this scientific conversation. How the human side of discovery, the doubts, the excitement, and the collaboration, drives the process of understanding our cosmic origins. For all the talk about models, data, and cosmic timelines, science is still a human pursuit. The James Webb Space Telescope may be an engineering masterpiece, orbiting 1 million miles from Earth, but its discoveries are interpreted by people with instincts, doubts, excitement, and biases. And when the first Webb data started hinting at galaxies that shouldn't exist, The reactions within the scientific community captured exactly what makes science both rigorous and alive. In the first weeks after those early images were released, astronomy forums and research channels exploded with conversation. Teams across the world began running calculations late into the night. Graduate students, professors, and postdocs traded spreadsheets and simulation plots like trading cards. Some could hardly contain their excitement. This was what they had waited their entire careers to see. Others urged caution, reminding everyone that the data were preliminary. "Let's not rewrite cosmology until we check the calibration," one researcher joked on social media. But even the skeptics couldn't hide a sense of awe. They all agreed on one thing: the universe had just become a lot more interesting. Inside NASA's Goddard Space Flight Center, at the Space Telescope Science Institute, and across institutions in Europe and Asia, the atmosphere felt electric. Teams were racing to confirm redshifts and measure spectra before anyone else. For months, the scientific servers were flooded with preprints, early papers uploaded before peer review, each one analysing some new Webb discovery. Some proposed that dark matter might behave differently in the early universe. Others suggested that the first stars formed faster, or that black holes seeded galaxies sooner than thought. The sheer speed of new ideas was dizzying. What had once been slow, methodical cosmology suddenly felt like frontier science again. Yet beneath the excitement was humility. Astronomers are used to being surprised by the universe. Every major telescope in history, Hubble, Chandra, Spitzer, has revealed something that defied expectations. Webb was no different, just more extreme. Many scientists compared the feeling to the early 1990s, when Hubble's first deep-field image stunned the world by showing thousands of galaxies in a patch of sky that looked empty to the naked eye. Webb was doing the same thing, but 10 times deeper, showing galaxies so far away that their light had travelled almost the entire age of the universe. When the first claims of impossible galaxies appeared, senior cosmologists advised patience. If something seems too good to be true, it probably means our models need better input, one said during a conference panel. Others emphasized the importance of skepticism. Webb's instruments were new, and the algorithms interpreting its data were being tested for the first time. The telescope was functioning perfectly, but human interpretation always carries risk. Calibrations could drift. Filters could overlap. Even something as simple as a background object contaminating a faint signal could lead to major misinterpretations. That skepticism wasn't cynicism, it was a form of respect for the process. Science moves forward by questioning itself, even when the data look thrilling. When early reports mentioned galaxies whose inferred ages exceeded the universe's timeline, most researchers didn't panic. They started checking assumptions. How were those ages being estimated? Were the models of stellar evolution appropriate for such an early cosmic epoch? Did dust or radiation bias the colour measurements? One by one, these questions shaped a community-wide investigation that's still unfolding. At the same time, scientists couldn't ignore what Webb was clearly showing them. Even after the cautious recalculations, the early universe still looked remarkably productive. Some researchers began organising collaborations to study the problem from multiple angles. Theorists, observers, and computational astrophysicists working side by side. Within months, new simulation projects were underway, trying to reproduce Webb's findings under different physical conditions. Theorists adjusted the dark matter density, tweaked the gas cooling rates, and experimented with more exotic scenarios. The result wasn't panic, but creativity. Cosmology was entering a new era of revision and refinement. The same way plate tectonics once redefined geology or quantum theory reshaped physics. For many astronomers, Webb's surprises also felt deeply personal. Decades of work had gone into building this telescope, and for some, it was the capstone of a career. Engineers who had spent years worrying about mirror alignments or cryogenic stability were suddenly watching their creation challenge the boundaries of knowledge. One scientist described it best. You spend your life designing an instrument to confirm what you think you know, and it ends up showing you what you didn't know you were missing. Public reaction added another layer. As headlines about galaxies older than the Big Bang spread online, scientists found themselves caught between fascination and frustration. On one hand, the attention was exhilarating. people around the world were suddenly talking about cosmology. On the other, the oversimplified claims risked turning nuanced discovery into clickbait. Many researchers took to social media to clarify that Webb hadn't disproved the Big Bang, only complicated its early stages. Some even saw it as an opportunity to educate, explaining how the telescope actually works and why apparent contradictions are often signs of progress. The real emotional core of this period was collaboration. Science thrives on competition, but Webb's findings reminded everyone that understanding the universe is a collective effort. Teams who might normally compete for telescope time began sharing data and cross-checking results. Conferences became standing room-only discussions, where theorists and observers compared notes in real time. The excitement was contagious, not just because the data were new, but because everyone could sense they were witnessing the early stages of a paradigm shift. Not a revolution that tears down old theories, but an evolution that makes them more complete. There's also a quiet, philosophical side to how scientists process moments like this. Many spoke about the feeling of humility that comes with seeing evidence of the universe's first sparks of structure. It's one thing to model galaxy formation on a computer, it's another to hold real data showing light emitted when time itself was young. For researchers who spend their lives buried in equations, Webb's images are a reminder that those equations describe something real, something vast and ancient that still has the power to surprise us. Even the disagreements, the debates about what the data truly mean, are signs of a healthy scientific culture. Disagreement is not division, it's the sound of progress being made. Each new Webb observation becomes a test not just of physics, but of how well humans can adapt to new knowledge. In that sense, the telescope is as much a mirror for us as it is a window to the universe. It reflects our curiosity, our fallibility, and our determination to keep asking questions, even when the answers don't come easily. And those questions are multiplying. If the early universe was as active as Webb suggests, then every part of our cosmic timeline may need adjusting. From how the first stars lit up the darkness to how fast black holes grew. Each of those puzzles has teams working right now to solve them. What unites them all is a sense of wonder. Webb didn't just give us new data, it reignited something fundamental in science. That feeling of discovery so powerful it reminds you why you started asking questions in the first place. But that excitement also leads to a logical next step. If these findings are real, and galaxies truly grew faster and earlier than our models predict, what does that mean for the universe as a whole? What new insights, or new physics, might emerge from accepting that the cosmos was ahead of schedule? Let's imagine for a moment that all of Webb's most extreme findings hold up. The galaxies are as old as massive and as chemically evolved as they seem. The distances are confirmed. The brightness isn't a trick of lensing or dust, and the models have been double-checked. In that case, the implications for cosmology are enormous, but not catastrophic. It wouldn't mean the Big Bang is wrong. It would mean that the way we understand the universe's early evolution is incomplete in a big way. If these ages are real, then the early universe must have been astonishingly efficient at turning raw material into structure. That would change the way scientists think about nearly every stage of cosmic history. Right now, models suggest that the first stars, known as population 3 stars, formed about 200 million years after the Big Bang. They were likely enormous, hundreds of times the mass of our Sun, made purely of hydrogen and helium. They burned hot, lived fast, and died in spectacular explosions that seeded the universe with heavier elements. But Webb's discoveries hint that this process may have started much earlier. Maybe the first stars formed within 50 million years of the Big Bang, not 200. That might not sound like a huge difference, but on a cosmic scale, it's like finding out the first cities on Earth were built while the planet was still cooling. If stars formed that early, then galaxies could have followed right behind. That would mean the seeds of structure were already in place, almost immediately after cosmic expansion began. Physicists would need to revisit the conditions of the universe during those first tens of millions of years. How did gravity manage to pull matter together so fast in such an energetic, expanding environment? It could mean that dark matter was more clumpy than we thought, gathering in dense halos that acted as shortcuts for galaxy formation. Alternatively, it might mean that the cosmic gas cooled more efficiently, collapsing into stars faster than our equations predict. Both possibilities would require rewriting parts of cosmology's rulebook. Another consequence would involve reionization, the era when the first stars and galaxies ionized the neutral hydrogen that filled the cosmos, making it transparent to light. Observations suggest this process ended about 1 billion years after the Big Bang. But if galaxies were forming and shining hundreds of millions of years earlier than we thought, that means reionization started sooner too. The early universe may have become transparent far earlier than our models show. That would change how we interpret the cosmic microwave background and how we measure the rate of cosmic expansion. The presence of heavy elements so early would also reshape our understanding of stellar evolution. If carbon, oxygen, and other metals existed just a few 100 million years after the Big Bang, it means the first stars lived and died at an incredible pace. The chemical enrichment of the universe would have happened much faster. That has cascading effects. It changes how gas cools, how planets form, and even how soon conditions for life might appear. It would mean that the raw ingredients for life, carbon and oxygen, were present in some regions of the universe within the first billion years of its existence. That's far earlier than anyone expected. Then there's the question of black holes. If galaxies really reached maturity so early, the massive black holes at their centres must have formed quickly too. Some might have grown from collapsing clouds of gas rather than from dead stars, bypassing the usual growth process entirely. That could explain why Webb has already found evidence of surprisingly large black holes in ancient galaxies. If these massive objects existed only a few 100 million years after the Big Bang, they could have acted as engines for rapid galaxy growth, pulling gas inward and triggering waves of star formation. The feedback between black holes and their galaxies might be far stronger and more fundamental than previously believed. All of this would also ripple through our understanding of dark matter and dark energy. These two invisible components dominate the universe's composition, but their exact nature remains mysterious. If structure formation happened faster, it could mean that dark matter behaves differently under high-energy conditions. Maybe it interacts weakly with radiation or has self-interactions that let it form dense clumps faster. Or perhaps dark energy, the force driving the universe's expansion, evolved over time, slowing expansion early on and accelerating it later. Even small changes to these parameters could reconcile Webb's findings with the Big Bang framework, while also hinting at new physics beyond what we know. One of the most exciting implications would be for cosmological inflation, the idea that the universe underwent a brief, exponential expansion right after the Big Bang. Inflation explains why the cosmos looks so uniform on large scales, but it also predicts subtle variations in density that later grew into galaxies. If the first galaxies appeared earlier and larger than predicted, it could mean those variations were stronger or differently distributed. That would prompt theorists to revisit the shape of the inflationary field, the mechanism that powered that early expansion. We might even be able to test those ideas through future measurements of gravitational waves, tiny ripples in space-time that inflation should have left behind. Another area that would see major revision is cosmic chronology. The age crisis Webb triggered could lead to recalibrations of the Hubble constant, the parameter that describes how fast the universe expands. Right now, measurements of the Hubble constant made using local galaxies disagree with those derived from the early universe's cosmic microwave background. If Webb's galaxies really formed earlier than expected, they could provide an independent test of that rate, helping to bridge the gap between early and late measurements. Resolving this Hubble tension would be one of the most significant breakthroughs in modern cosmology. Philosophically, the implications are profound too. If the early universe could organize itself into galaxies so rapidly, it challenges our intuitive idea that complexity takes time. We tend to think of evolution, biological or cosmic, as a slow process. But Webb's data suggests that the universe can move from simplicity to structure in a cosmic heartbeat. It's a humbling reminder that time is relative not just in physics but in creation itself. The cosmos, even at its youngest, wasted no time in becoming rich and intricate. If these results hold, future models of the universe will include a revised timeline that begins the process of structure formation almost immediately after the Big Bang. The first stars might have flickered on within tens of millions of years. Galaxies might have reached substantial mass within a few 100 million, and by the time the universe was 1 billion years old, it might have already contained the fundamental ingredients for the worlds that would one day orbit stars like our Sun. For scientists, that realization would be exhilarating rather than alarming. The Big Bang would still stand as the beginning, but it would now describe an even more dynamic and creative process than anyone imagined. Far from weakening cosmology, Webb's discoveries would make it deeper, forcing us to see the Big Bang not as a single event frozen in the past, but as the start of an ongoing transformation that still shapes the universe today. And if those ages are real, it also changes something about us. It reminds us that we're part of a universe that builds itself quickly and efficiently, a cosmos that seems eager to create structure and light. The fact that we can now see those first sparks of order through Webb's mirror is not a challenge to science, it's a triumph of it. But as with every major discovery, the next question follows naturally. If this is true, what does it mean for the balance between discovery and perception? How do we keep the science precise while the world races to interpret it? And how do we separate legitimate paradigm shifts from overhyped misinterpretations? That tension between excitement and accuracy lies at the heart of the next part of this story. Whenever a discovery challenges what we think we know about the universe, there's a moment when science and storytelling collide. One side is patient, data-driven, and careful about uncertainty. The other wants a headline, a dramatic revelation that everything we thought was true has just been shattered. The James Webb Space Telescope's early findings landed right in the middle of that collision. To the public, it looked like a revolution. To scientists, it was something far more interesting, the beginning of a recalibration. This difference in interpretation isn't new. Every major leap in cosmology has followed the same pattern. When Hubble proved that galaxies were moving away from us, newspapers declared the discovery of a cosmic explosion. When Einstein published general relativity, many journalists described it as tearing down Newton's laws. In truth, neither discovery destroyed the previous framework, they refined it. Newton's equations still describe most of the motion in our solar system. Einstein simply showed they were part of a larger story. That's what's happening with Webb. It's not tearing down the Big Bang, it's expanding what that theory covers. The Big Bang has survived every test thrown at it because it's built on evidence that's independent and consistent. The cosmic microwave background, the abundance of light elements, and the redshift of galaxies. Webb's discoveries fit within that foundation. They don't contradict the expansion of the universe or its age. What they do challenge are the assumptions we made about how quickly the universe organised itself afterward. And that's a very different kind of challenge. It's not a revolution that breaks the rules, it's a refinement that adds new ones. But the temptation to frame every major discovery as a revolution is understandable. Human beings crave dramatic turning points. Everything we know is wrong makes a better headline than our models are being updated. Yet the latter is how science actually progresses. It's incremental, self-correcting, and constantly re-evaluating its own limits. Most breakthroughs are not clean breaks from the past, but extensions of it. Moments when an existing theory is stretched to accommodate new information. Webb's findings are one of those moments. They reveal that the universe was more efficient, not that it came from somewhere else. Still, misinterpretation has its own power. The viral idea that Webb had found something older than the Big Bang may be wrong scientifically, but it captures a feeling that's deeply human, the desire to reach beyond beginnings. People want to believe that there's something before everything, that the universe hides a deeper secret just out of reach. The irony is that this curiosity, the same impulse that makes headlines exaggerate, is also what drives science forward. If nobody asked impossible questions, Webb would never have been built. Inside the scientific community, the difference between misinterpretation and revolution comes down to one word: verification. True revolutions survive scrutiny. They hold up under replication, multiple instruments, and independent analysis. Most initial crises in physics eventually dissolve once the data are refined. The current tension over Webb's galaxies will go through that same process. If the results hold after years of follow-up observations, they'll be integrated into a new version of our cosmic story. If they don't, they'll still have served their purpose, forcing scientists to strengthen their methods and confirm their models. Either way, progress happens. There's also a sociological layer to all this. The modern information ecosystem moves faster than peer review ever could. Data released on a preprint server can spark global speculation overnight, while the careful process of verification takes months or years. That time gap is where misinterpretations grow. A few ambiguous phrases in an academic paper can become a viral narrative by morning. Scientists know this, which is why many now communicate directly with the public through blogs, podcasts, and social media. They want to explain discoveries before they're distorted. The web era is pushing that kind of communication to new importance. When the universe reveals something unexpected, clarity is the best defense against confusion. It's also worth remembering that misinterpretation and revolution aren't opposites. They are often the same story told at different speeds. What looks like hype today can become consensus tomorrow, once the evidence catches up. When the cosmic microwave background was first detected in the 1960s, it was dismissed by some as noise from a faulty antenna. Now it's one of the pillars of cosmology. The lesson is patience. Science doesn't move in viral cycles, it moves in decades. If Webb's data do mark a revolution, it will be a quiet one, a shift in how we think about the timeline of creation. Instead of a slow rise from chaos to order, the universe may have leapt into complexity almost immediately. That change in understanding is profound enough without rewriting the laws of physics. It shows that the cosmos has always been more efficient than we give it credit for, and that our theories are only as complete as the technology we use to test them. Webb didn't end the Big Bang model. It showed that the model is still alive, flexible, and ready to absorb new truths. At the same time, these discoveries remind us why revolutions in science are so rare and so valuable. They don't come from rejecting the past, they come from deepening it. Einstein's relativity didn't overthrow Newton, it extended his ideas to new domains. Quantum mechanics didn't erase classical physics, it revealed a layer beneath it. In the same way, Webb's revelations don't undo the Big Bang, they reach closer to its moment of birth. The boundary between misinterpretation and revolution is where science thrives. It's the space where excitement meets evidence, where the imagination runs ahead of certainty, but doesn't abandon it. Webb sits precisely in that zone. It gives us data that both astonish and perplex, forcing us to question everything just enough to make progress. That balance between wonder and discipline is what keeps science honest. So while the headlines might scream that everything we know is wrong, the truth is subtler and more satisfying. Everything we know is incomplete, and that's what makes discovery possible. Every new observation from Webb fills in one more piece of the puzzle while revealing how much more there is to find. Misinterpretation fuels curiosity. Revolution refines understanding. Both play their part. The best way to see it is this: the Big Bang isn't under threat. It's being illuminated. The oldest light in the universe is now being reinterpreted through Webb's eyes, and with it, our sense of cosmic history is becoming richer. What we're witnessing isn't science collapsing, it's science doing what it's meant to do: evolve. And that evolution leads naturally to one more question that continues to fascinate scientists and the public alike. If Webb hasn't found anything older than the Big Bang, could it ever? Is it even possible, in principle, for a telescope to detect traces of something that existed before time began? It's an irresistible question. If the James Webb Space Telescope can see billions of years into the past, could it ever see beyond the Big Bang itself? The short answer is no, not directly. Webb can't look past the Big Bang for the simple reason that there's no light to see from before it. The telescope, powerful as it is, depends entirely on photons, particles of light. And before the Big Bang, according to our current understanding, light as we know it didn't exist. Time, space, and the laws that govern them all came into being with that event. But the longer answer, the more interesting one, is that Webb might one day help us find indirect clues about what happened before our observable universe began. To understand why, it helps to picture what the universe was like at the earliest times Webb can actually observe. The telescope is designed to detect infrared light, the stretched, red-shifted remnants of radiation emitted by the first galaxies and stars. That means Webb can peer back to roughly 300 million years after the Big Bang. It can't go further because before that, the universe was opaque. About 380,000 years after the Big Bang, protons and electrons combined to form neutral hydrogen atoms, releasing the cosmic microwave background, the oldest light we can see directly. Before that moment, the universe was a dense fog of charged particles that scattered light in all directions. It wasn't transparent, and no telescope, no matter how advanced, can see through that barrier with normal light. But that doesn't mean the story stops there. While Webb can't detect light from before the Big Bang, it can look for evidence that something might have left fingerprints on the universe we see today. Imagine ripples in a pond after a stone has been thrown in. Even if you didn't see the stone, you can infer that something caused those ripples. In cosmology, those ripples might take the form of subtle irregularities in the cosmic microwave background, the large-scale structure of galaxies, or even gravitational waves. Distortions in space-time itself. Webb isn't built to detect gravitational waves directly, but its observations could help confirm their effects by mapping how matter was distributed in the early universe. One of the most promising ideas is that remnants of a pre-Big Bang state might be encoded in the patterns of cosmic structure. If our universe emerged from a bounce, a previous cycle of contraction and expansion, it might have inherited some of that earlier universe's features. Those features could show up as slight asymmetries in how galaxies are distributed, or as temperature fluctuations in the cosmic microwave background that don't quite match random noise. Webb's observations of very early galaxies can help test whether such irregularities exist and whether they're consistent with the predictions of bounce or cyclic cosmologies. Another intriguing possibility involves cosmic inflation, that brief period of exponential expansion right after the Big Bang. Inflation smoothed out the universe but also froze tiny quantum fluctuations into the fabric of space itself. Those fluctuations became the seeds of galaxies, clusters, and cosmic filaments. If there were influences from a time before inflation, they might subtly alter that pattern. By studying the clustering of the earliest galaxies and comparing it to what inflation predicts, Webb could indirectly test whether there was a prehistory to our universe. Then there's the question of dark matter and dark energy, two mysteries that dominate modern cosmology. If either of these forces existed in a different form before the Big Bang, their fingerprints might still be visible today. For example, if dark matter particles interacted differently under the extreme conditions of a pre-Big Bang universe, they could leave anomalies in how early galaxies formed or in how matter clumps together. Webb's ability to map that clumping at unprecedented precision might reveal hints of physics that extend beyond the Big Bang's beginning. Some theorists go even further, proposing that our universe is part of a multiverse, one bubble among many in a larger cosmic foam. If that's true, interactions between universes could, in theory, leave marks on ours. For instance, if another universe bumped into ours early in its history, that collision might have left a circular pattern in the cosmic microwave background or an unusual alignment in galaxy distributions. Webb won't directly see another universe, but it could provide data to test these hypotheses more precisely than ever before. In short, Webb's power isn't in seeing before the Big Bang, but in helping us trace how the universe evolved immediately after, and in testing whether the fingerprints of something older still linger. It's a bit like forensic science. You can't observe the crime itself, but you can reconstruct what happened by studying the evidence left behind. Every faint galaxy Webb discovers is a clue about what conditions were like when time itself was young. And that's what makes this telescope so special. It doesn't need to break the laws of physics to rewrite the story of creation. By refining our understanding of the first few 100 million years, Webb tightens the constraints on any theory that dares to reach beyond them. If a model predicts that something existed before the Big Bang, Webb's data can either support or rule it out based on what we actually see. In that way, it acts as both explorer and judge, not seeing beyond the beginning, but defining where the beginning truly lies. For now, the cosmic curtain at 380,000 years after the Big Bang remains opaque, but technology continues to advance. Future missions, like the proposed next-generation gravitational wave observatories and radio telescopes designed to map hydrogen from the dark ages, might one day peer even closer to that mysterious threshold. When that happens, Webb will have set the stage, having shown us exactly how far light can carry us back into our cosmic past. In the end, the quest to see before the Big Bang is less about sight than about understanding. The telescope has already proven that the universe's first chapters are full of surprises. Whether or not we ever glimpse the pages before them, we now know that the story of creation is more intricate, more ambitious, and more beautiful than we ever imagined. Webb's mission isn't to end the mystery, it's to show us that there's always another layer waiting to be uncovered. And that realization brings us to what might be the most awe-inspiring truth of all. Even if we can't see beyond the Big Bang, what Webb has revealed about what came after is already extraordinary. The universe wasn't hesitant, it was exuberant. It didn't tiptoe into existence, it raced. Which leads naturally to the next chapter. Not about what might have come before, but about how the universe that followed became so astonishingly productive so quickly. When you strip away the headlines and the hype, what Webb has truly shown us isn't that the Big Bang was wrong, it's that the early universe was a lot busier than we ever gave it credit for. The real story isn't about galaxies that somehow existed before time. It's about how fast the universe learned to build. Webb's discoveries reveal a cosmos that, within a few 100 million years of its birth, had already gone from a featureless soup of particles to a sprawling web of stars, black holes, and galaxies. That speed alone is breathtaking. To appreciate how remarkable that is, think about the scale of what had to happen. Right after the Big Bang, the universe was a hot, uniform fog of hydrogen and helium. There were no stars, no structure, just expanding gas and energy. For galaxies to exist only a few 100 million years later, a series of complex steps had to unfold almost immediately. Tiny fluctuations in density, random quantum ripples from the earliest moments, had to grow under the pull of gravity. Those ripples became slightly denser patches of gas, which began collapsing into clumps. Inside those clumps, the first stars ignited. Those stars exploded, spreading heavier elements and triggering new waves of formation. Within what feels like the blink of a cosmic eye, the universe went from chaos to complexity. Webb has now made it clear that this transition didn't take billions of years. It took hundreds of millions. That's nothing in cosmic time. If the entire history of the universe were compressed into one calendar year, the Big Bang would happen on January 1st, and our present day would fall on December 31st. By that scale, the first galaxies would have appeared before the end of January. The universe was already glowing with light while it was still in its infancy. The speed of that transformation is rewriting how astronomers think about the physics of the early cosmos. It means that the processes driving star formation, black hole growth, and chemical enrichment were far more efficient than models had assumed. Webb's images of compact, bright galaxies suggest that matter collapsed into dense regions much faster than expected, perhaps aided by unusually active dark matter or intense feedback from the first generation of stars. These stars, massive, short-lived, and powerful, would have pumped radiation and heavy elements into their surroundings, creating the perfect conditions for rapid galactic growth. In effect, the early universe was a construction zone, operating at full speed. Galaxies were forming, merging, and feeding black holes in a kind of cosmic rush hour. Webb's data show that by just 500 million years after the Big Bang, galaxies already came in a wide range of shapes and sizes. Some were small and irregular, while others were compact and surprisingly luminous. A few were so large that they rivaled mature galaxies seen billions of years later. It's as if the universe didn't go through a gradual childhood at all. It jumped straight into adolescence. This rapid development also means the early universe was a far more interconnected place than we once thought. Gravity wasn't just pulling matter together, it was doing it cooperatively. Galaxies interacted, merged, and recycled material. When one galaxy's stars exploded, the shock waves compressed nearby gas clouds, sparking new rounds of star formation. The entire cosmos was learning how to build itself through feedback loops, each generation of stars paving the way for the next. Webb's observations of early starburst regions, areas of intense star formation, are snapshots of that learning process in action. Another fascinating outcome of Webb's discoveries is how they blur the boundary between what we call early and modern galaxies. Previously, astronomers thought it would take billions of years for galaxies to form stable disks or spiral structures. But Webb has found candidates that already show hints of order, a degree of symmetry, maybe even rotation. That's like finding skyscrapers in a civilization you thought was still inventing the wheel. It suggests that the forces shaping galaxies today were already active from the very start. All this activity has implications far beyond galaxy formation. It affects the chemical evolution of the universe, the way simple elements turned into the complex ingredients of planets and life. Every heavy element in your body was once forged inside a star. If stars were forming and dying earlier than expected, That means the universe was creating those elements earlier too. By the time our own galaxy formed billions of years later, it was already inheriting a universe rich in the materials for complexity. In a sense, Webb's discoveries pushed the potential timeline for habitability further back than ever before. The universe might have been ready for life, at least in principle, long before Earth existed. But perhaps the most striking takeaway is philosophical. The universe, as revealed by Webb, doesn't appear hesitant or slow to organise itself. It's eager. As soon as the conditions allowed, it began weaving complexity out of simplicity. That enthusiasm for structure, gravity shaping chaos into beauty, seems to be a defining property of nature itself. The fact that Webb can show us that process happening in real cosmic time, billions of years ago, turns what might have been an abstract idea into something tangible. It also changes how we think about the Big Bang. The event wasn't just a beginning, it was a set of conditions designed for creativity. Matter didn't need billions of years to figure out what to do. It started assembling itself right away. If anything, Webb's discoveries make the Big Bang more impressive. It wasn't a simple spark that faded into calm. It was the trigger for an explosion of complexity that filled the cosmos almost immediately. Scientists are now racing to understand what made that possible. Were there feedback mechanisms we haven't modelled yet? Did dark matter play a bigger role in structuring the universe? Were the first stars fundamentally different from anything we see today? Every one of Webb's deep field images adds a clue, and with each clue, the story of the universe's first billion years becomes clearer and more extraordinary. So when you hear that Webb found something older than the Big Bang, remember, it didn't. What it found was something better. The story of how the universe became mature, almost overnight. The Big Bang gave it the ingredients, but what came next was a cosmic sprint towards structure and light. That's the real headline. And yet, as complete as that sounds, there's still more to the story. Webb is just beginning its mission, and every new batch of data reveals galaxies we hadn't seen before, each one pushing the boundary of how far back we can look. The deeper we peer, the more the universe's own pace surprises us. The next step is to understand how these discoveries fit into the grand arc of cosmic evolution. How those early, frantic years gave rise to the vast, structured universe we inhabit today. The James Webb Space Telescope hasn't just rewritten a few lines of cosmology textbooks. It started a new chapter in how we explore the universe. For decades, astronomers worked with models built on assumptions, simulations, and the best data Hubble and ground-based observatories could provide. Those models served us well, painting a coherent picture of a universe born 13.8 billion years ago that slowly cooled and organised itself into stars, galaxies, and everything else we see today. But Webb changed the tempo of that story. It revealed that the universe didn't take its time, it sprinted into structure almost immediately. That realisation doesn't end the Big Bang model. It extends it, and it's transforming the future of cosmology. To understand what this means going forward, it helps to remember what Webb really is: a time machine. By collecting infrared light, the faintest, most stretched out wavelengths from the earliest galaxies, it allows us to see across almost the entire history of the universe. With every new observation, it's giving cosmologists something they've never truly had before: a detailed panoramic look at the universe's formative years. The first billion years after the Big Bang used to be a dark zone, a period we could only simulate. Now it's a window we can finally look through. That's why the telescope's first few years of operation have already sparked hundreds of new research programs. Astronomers are using Webb not just to count distant galaxies, but to dissect them, measuring their chemical compositions, star formation rates, and even their internal motions. The results are helping refine every major branch of cosmology: galaxy evolution, dark matter physics, cosmic inflation, black hole growth, and even the origins of the elements that make planets and life possible. One of the biggest shifts Webb has triggered is a move from theory-driven to data-driven cosmology. For years, simulations were our main guide to the early universe. Researchers would tweak parameters like dark matter density, gas cooling rates, and supernova feedback until the results matched what we could observe nearby. But Webb's unprecedented detail means those simulations can now be tested directly against reality. Theorists are already recalibrating their models to reproduce the kinds of galaxies Webb has found: dense, bright, and fully formed, at record-breaking distances. Those refinements will feed back into everything from star formation theory to the models used to measure the universe's expansion rate. Another major consequence of Webb's discoveries is how it's reshaping our understanding of cosmic chronology. If galaxies were forming faster and earlier than expected, then the timeline of reionization, the era when the universe became transparent to light, may need revising. Scientists once thought that process took hundreds of millions of years. Webb's data suggest it could have happened much faster. The telescope's upcoming surveys aim to map that transition in detail, showing how light gradually reclaimed the universe after the cosmic dark ages. Understanding reionization isn't just an academic exercise. It's key to knowing how galaxies like ours eventually formed, and how the universe became a place where light could travel freely. Perhaps the most exciting part of Webb's impact is how it bridges cosmology and astrophysics. For a long time, those fields operated almost separately. Cosmologists focused on the large-scale structure of the universe, while astrophysicists studied the detailed behavior of stars and galaxies. Webb sits perfectly at their intersection. Its deep-field images reveal entire populations of early galaxies while also resolving their individual properties. It's connecting the dots between the physics of small-scale star formation and the grand-scale evolution of the cosmos. In other words, it's showing how local physics built the universe itself. Looking ahead, Webb is also laying the foundation for the next generation of cosmic exploration. The data it gathers today will guide the design of future missions, space telescopes that could peer even further back or detect phenomena Webb can't. Projects like the Nancy Grace Roman Space Telescope and the European Space Agency's Euclid mission will map the large-scale structure of the universe with incredible precision. Others, like the Laser Interferometer Space Antenna, LISA, will listen for gravitational waves from the earliest cosmic events. Together, they'll give us a multi-messenger picture of the universe, one that combines light, gravity, and particles to tell a complete story from the Big Bang onward. Webb's influence also reaches into particle physics. If its observations continue to show that galaxies formed faster than predicted, physicists may need to rethink what dark matter is made of or how it interacts. That could, in turn, inspire new experiments on Earth: underground detectors, collider searches, and laboratory simulations of cosmic conditions. Cosmology and particle physics have always been linked by their shared goal of understanding the universe's first seconds. Webb's data could provide the clues needed to unify those scales, connecting the largest cosmic structures to the tiniest subatomic particles. There's also a cultural shift happening within science itself. Webb's discoveries are encouraging a new level of openness and collaboration. Many of its datasets are released publicly, allowing researchers around the world to analyze them simultaneously. The result is a global scientific conversation happening in real time, with teams confirming, challenging, and refining each other's interpretations. That openness ensures that progress doesn't depend on a single institution or country. It's a collective human endeavour to understand our shared origin. And beyond the scientific world, Webb's images have reignited public fascination with the cosmos. Its first deep-field photo, thousands of galaxies captured in a single frame, was shared by millions of people. Each glowing speck represents a story billions of years old, a reminder that the universe's history is written in light. By turning abstract equations into something visible and beautiful, Webb has done something even more profound than rewriting textbooks. It's made people care about where we came from again. The future of cosmology now feels wide open. With every observation, Webb brings us closer to answering questions that once seemed unanswerable. How quickly can structure form? What role did dark matter play in shaping the first galaxies? How did black holes grow so fast? And maybe one day, what truly happened at the very moment the Big Bang began? Each answer leads to another question, and that's exactly how science should work. Ultimately, Webb's legacy will be twofold. It's a machine for discovery, yes, but it's also a reminder of how discovery happens. Knowledge doesn't advance through certainty. It advances through curiosity, through confronting the unknown and being willing to revise what we think we know. The telescope is not a symbol of final answers, but of ongoing inquiry. It shows that the universe is not static, and neither is our understanding of it. So what does Webb mean for the future of cosmology? It means that we're living through a transition as profound as any in the history of science. The early universe, once hidden in darkness, is now an open field of study. The laws that govern it are being tested, refined, and rewritten in real time. And the story of creation, the one that began with a single burst of energy 13.8 billion years ago, is no longer a mystery we can only imagine. It's something we can now observe, analyse, and, for the first time, begin to truly understand. That's the quiet revolution Webb has delivered. It didn't disprove the Big Bang, it gave it life, texture, and motion. The universe isn't just expanding in space, our understanding of it is expanding too. And with every photon Webb collects, that expansion continues, not into the past, but into the future of what we're capable of knowing.